Hi, my name is Ashley Arcidiacono, and I'm a graduate from the Hansen Research Group at Florida State University. And I'm excited to share with you one of our recent publications on how metal linking ions can impact the structure and energy transfer efficiency in ion-linked multimolecular assemblies. Metal ion-linked bilayers are a modular way to build multimolecular assemblies on surfaces with uses ranging from solar energy conversion to sensing. Most of these applications depend on energy or electron transfer between the layers. But what's less understood is how the choice of linking metal ion itself actually affects the structure and the transfer dynamics. And this paper addresses that question directly using a bilayer system as a model. The model system built is on mesoporous zirconia. A phosphonated anthracene derivative A is first anchored, then a metal ion, either zinc, zirconium, or lanthanum, links a second layer carboxylated porphyrin on top. And this produces these three distinct films where the metal ion linkage imposes either a 4, 6, or 9 coordinate environment. Surface coverage and orientation are then assessed by adsorption isotherms and polarized attenuated total reflection. And then energy transfer is measured with transient absorption spectroscopy. And all these results are compared against a geometric model that calculates FRED efficiency across all the possible bilayer orientations. Adsorption isotherms for P on the zirconium anthracene metal ion films show that a maximum surface coverage follows the order of zinc, then zirconium, then lanthanum. The metal ion clearly limits how much porphyrin can load onto the surface, but the ordering doesn't track with ion size, charge to size ratio, or hard-soft acid-base character. The mechanism behind this trend remains unsolved, but to keep this loading difference from confounding the transfer mechanisms, all samples are standardized to a 10-to-1 anthracene to porphyrin ratio. Singlet energy transfer from excited state anthracene to porphyrin proceeds through a Forster resonance energy transfer mechanism. And it's isolated by exciting the films at 360 nanometers, which is a wavelength absorbed mostly exclusively by anthracene, and following the transient absorption signal. Because there's minimal direct excitation of porphyrin at this wavelength, the growth of the porphyrin excited state signal in the transient absorption spectrum can be directly assigned to FRET from the excited state of anthracene without needing to deconvolve a competing direct excitation pathway. Fitting that signal for growth of the three linked bilayers gives us distinct lifetimes and FRET rates, where zirconium and zinc yield essentially the same FRET rate or signature lifetimes, while lanthanum is slower by close to a factor of 2. And this tracks with the differing coordination chemistry of the three ions, where zinc is typically 4 coordinate, zirconium 6, and lanthanum 9. And this imposes a distinct linking geometry for the lanthanum bilayer. The metal ion doesn't change the mechanism of energy transfer. It always remains FRET dominated, but it does modulate the FRET rate through this structure. And since FRET efficiency depends steeply on the distance and the relative orientation between donor and acceptor transition dipoles, a twofold change in rate implies a meaningfully different average separation or orientation between the anthracene and porphyrin in the lanthanum-linked film. Polarized ATR measurements yield the mean tilt angle of each layer relative to the surface. These angles differ measurably depending on which metal ion links the bilayer, producing distinct proposed geometries for the zinc, zirconium, and lanthanum linked assemblies shown here. The identity of the linking ion measurably reorients the porphyrin layer, not just how much of it adsorbs. And because polarized ATR can't resolve the azimuthal angle, each geometry is only one of the several structures consistent with the data that we've collected. So we pair these conclusions with a computational check. To connect structure to rate, we calculate theoretical FRET efficiency across full space of possible bilayer geometries for each metal ion. And then we map where theory and experiment agree within 1%, and that's the black band you see on these spheres. We found a limited set of geometries reproduce the measured FRET efficiencies, and those geometries are consistent with, though not uniquely determined by, the PATR tilt angles, giving independent structural support to the proposed models. So across all of these techniques used, transient absorption, polarized ATR, and geometric calculations, the same picture emerges, which is that the metal linking ion shapes the bilayer structure through both how much porphyrin can load and how this porphyrin is oriented. And the structural sensitivity carries through to singlet energy transfer, where we see that the lanthanum-linked films transfer energy roughly twice as slowly as zinc or zirconium-linked films. Together, this establishes metal ion selection as a practical, structure-based handle for tuning excited state energy flow in these multi-layer architectures.